So it's so I have this product that I've put together. I retired from Microchip April of 2018, and then I started working on the project properly. And let me see. This is my presentation. And so now I'm selling the product on Tindy just recently. I've sold about 30 systems total. And Greg Nutt got in touch, and he started asking questions about the board, and he bought a couple of pieces of hardware, and in a matter of, I don't know, what, a week or week and a half, did a preliminary report of NUTX to the board. And he said, I'll have more time to spend on this when I get back from this conference. I said, oh, what conference are you going to? And so he told me about this. I said, gosh, that sounds good. It's like lots of interesting people doing interesting things, and a whole bunch of people I've never met before in a place I've never been. So let's go talk to them about this, and maybe somebody will like it. So that's what I did. So what is it? It's a very simple personal computer. Modern construction, contemporary interfaces, so you can plug it together with things and you can actually talk to it, but it acts and looks and feels and has that familiar, mid-'80s microcomputer, personal computer feel. So, I would say that you have about a 1985 processor and OS functionality and performance. It's a 50 megahertz EZ80, so that's pretty good. Zilog never stopped making the Z80s. They made many different variants, and the EZ80 is the one where they finally got it right. So there's no paging, no bank switching or anything like that. It's just a big flat address space. It's got a big real mode, just like the x86s have a big real mode. You flip these bits, and then suddenly you have 24-bit addresses, and all your 16-bit registers turn into 24-bit registers, and it just works very, very simply. So this computer is inexpensive, it's modular, it's portable, and it's maker-friendly. I sort of wanted to make a cross between like vintage embedded makers. So I like the maker movement, I like the retro movement, I like the old PCs. So let's do it all together, because I am kind of tired of how complex our personal computers are today and how difficult it is, and every 3 weeks I have to install another level of the operating system which breaks all the old applications. And it's like, gosh, if I have to do all this work, why don't I just write the software and make it all work myself? So I was retiring, and I decided I wanted to build the computer I wanted. So I wanted to make the machine for the system I wanted to create on the machine, and I wanted to create the system that would work on that computer. So the two things kind of conspired together in order to create the aesthetic I wanted. This is a joke, but with the right recipe, we don't really need more than 640K. With
Bill Gates.
But we can have 16 megs in this particular platform. And then the last couple of things are sort of like statements about personal freedom and aesthetic and creativity and imagination. It gets kind of tiring when you have to keep on changing things and doing work just to stay compatible with everything else. But maybe the quality of the software that you are having to take is not so great, and you have to kind of make these compromises. And there is a certain cost to staying in conformance with the rest of the world. So, well, here's a group of people who, none of you are using NUTX because somebody told you to. You're using it because it works, and it works better. And you're putting together systems that really have to work. And so you're making your choices based on your experience of what works well and which direction you want to go. And maybe you have to do some of the work yourself, but at least in an environment that you've chosen and that you like and that you think is rational. So that's the same kind of attitude I wanted to bring to my next personal computer. So it's like the early microcomputers in that it's essentially kind of a single-threaded metaphor. It's a text-based UI. It's DOS text machine, essentially. We have a simple, real memory model. The system architecture is a CPU and a terminal and a disk and some extra I/O. You also have a very narrow connection to the OS in the machine, which makes things very portable because there's really not a lot of crossing a large mosaic broad interface. You know, sometimes in our programs today, we have hundreds and hundreds of library calls that mean that you need to have all of these different bindings, and they have to be at the right level, and they all have to be compatible with each other because there's stuff that's happening behind the scenes. And so I kind of miss some earlier models of computing where you're doing most of the work in your program, and your connection to the operating system is kind of simple and not really challenging, and you're spending most of your time in your own program. So programs like this can be trivially portable, and your program sort of does everything that needs to be done and owns the machine. Or you can dispense with everything I've said about software and just say that this is pretty nice hardware that's inexpensive and fast and cheap, and you can do what you want with it. So old style computing, vintage, classic kind of feel, but modern materials. So it's a 50 megahertz microcontroller, microprocessor system on chip. It's kind of a cross between a microcontroller and a microprocessor because it's a system on chip microcontroller with all the GPIO and embedded peripherals and things that you would expect on any of the other microcontrollers. But it's also got an address bus, and external RAM is possible. So the buses that it exports are classic old microprocessor kind of buses. So it makes it a very easy system to build a system around. The business card is 4-layer surface mount. Got USB UART, supports USB keyboard, SPI micro SD, microcontroller style GPIOs for all your Arduino kinds of things. There's a high density connector on the back of that CPU card, as you can see, that plugs into that expansion board. There's no jumpers, everything is kind of like sensed and figured out, and it's pretty low power. So that's just about the machine itself. I've kind of adapted this presentation because I've given this talk to several other Lisp and functional programming groups, where what I'm talking to them about is they're programming in this Lisp kind of AI, kind of like this world, but now they see all this fun stuff that people are doing with hardware, and they'd like to get their fingers into the hardware too. So this implementation and dialect of Lisp is a way that they can reach hardware, and they can do the Arduino kind of thing, but stay in their comfort zone of Lisp programming. Or I go to talk to people who are doing embedded control and working with things like C++ or MicroPython on microcontrollers, but would like to have another, a little bit more leverage in an interpretive kind of rapid prototyping environment. But today I decided to also talk just a little bit about the platform, because although this system is Lisp on bare metal, it also can run on top of this Lisp implementation is standard C, it's very portable, and it can also run on Linux, and therefore it can run on NUTX. And so it will be running on NUTX pretty soon, now that NUTX is on the platform. I think it's going to be kind of a trivial port. So why do I like Lisp? How many of you have experience with Lisp in the room? So some of these things will resonate with you. When you get a Lisp program together, working code works everywhere, every time. Referential transparency. It's like you write working code. If it doesn't touch, mutating state, you pick up that code, drop it in another place, it means exactly what it meant in the other place. It's just, it's just portable and it works. You develop small functions, you get done, you file them away, and you move on. The other thing is that you tend, in the work style and in the way that you develop programs in Lisp, you tend to really have to think things through and understand what your program is doing. And you do most of the debugging in your head before you write the code. It's kind of your program becomes kind of a statement of the problem in its most essential terms. And you wind up thinking through in terms of just evaluating the expression of the program itself, but also if you understand the underlying interpretive model of the engine that's doing the expression evaluation, you are kind of working through the mechanics of how your program will operate. And you can reliably reason about it in a simpler way than a lot of other languages. So these programs are brief and they have high semantic energy density. And a few of the language artifacts in this language, closures, continuations, and macros, when you have those things, you basically have everything you need to extend the language in the language itself. So it's a functionally complete language. Now, I'm going to just kind of zip through some of these Lisp language concept, implementation details. If any of them sound interesting to you, just put up your hands and ask, and we'll stop and we'll dwell on that. Otherwise, I'll just kind of roll through them and we'll get to some more concrete stuff in a little while. So, but another statement about Lisp systems, it's probably the smallest and easiest system that you can build that's functionally complete, these Lisp families of languages. MakerLisp itself, I think it's pretty small, I think it's pretty light, I think it's pretty fast. It's got a JIT inside, so it JITs to threaded code, and it's fairly efficient in the way it operates. It's based on a virtual machine model called SECD, which stands for Stack Environment Command or Control, or any other word you want to use that starts with C, which is really basically your program instructions, and dump is your continuation, your stack of continuation frames, or the program's continuation. It's written in C, but only a very tiny core language is written in C, which keeps the amount of C, it's about 5,000 lines, small, and then everything else is written in Lisp functions and Lisp macros. The dialect itself is a blend of Common Lisp in terms of primitives and spellings and semantics of low-level functions, and the Common Lisp low-level macros. But it has the scheme evaluation model, and it has a C standard library and C numerics. So it's a kind of a practical mix. And it's very good for small machines, and it has been good for this machine. And if you are an enthusiast of Forth, you might find the development style in an interpretive system like this very similar to what you're used to. Just some facts about the machine that I've already kind of enumerated. When I would take this to shows, people would say, is that Arduino or is that Raspberry Pi? No, it's something in between. But you could also think of it as a modular, breadboard-connected 1980s era PC. These are some details about, interesting tidbits of, this particular Lisp dialect. Low-level macros are extremely powerful, and I don't know if I've said it in this, they're kind of like a brain teaser sometimes to work out. But it's sort of like doing integrals, it's a little tough on the brain, but once you've sorted it out, you really have a lot of power. Anyone want to hear more about macros and how macros work in Lisp?
Probably before the break. Probably in the break.
Yeah, that's fine. All of these things can be talked about. So some features and utilities that make it a little easier to program in this particular Lisp. I have an expander that shows how all the macros expand, so you can, and I'll show that when we set up the machine and do some demos. There's a function tracer, there's a low-level debugger, and there are many examples of the language use because so much of the system is written in the language. Of course, to make this thing useful on a machine like this, you want to have direct access to the machine registers from the language itself. So you're only a couple of Z80 instructions away from touching the hardware at any point. There is no cache, there is no virtual memory. there's just SRAM. It's kind of funny how I chose this processor. It's nice that it's Z80 based, and that's kind of a bonus, but that's not how I chose it or why I chose it. I'm a big fan of MIPS and similar processors like RISC-V and things like that. So when I was trying to figure out what processor I wanted to base this on, and I looked at many different single board computers and different things, but I said, I'm driving myself crazy. It's like, it's not so much that the ISA matters. I just need to find the right thing that I can build the system architecture around. And I said, okay, I'm going to eliminate all biases. I'm going to close my eyes and do a blind search on DigiKey. I just need it to cost less than $10, and I need to be able to access at least a megabyte of memory. And what came up but 2 Z80 variants? So it's like, okay, that's the processor. And bonus, I can run CPM. So, so that's how that got chosen, and it was just kind of fortuitous. But a few other features here is that any break, any exception in the system can be intercepted by placing a Lisp handler there. I have kind of an interesting garbage collection mechanism that is very low latency. I wouldn't say that it's real time and it's completely deterministic, but because in point of fact, there's almost never any garbage to collect, garbage collection is a very low impact on the system. And we can talk about how that happens. Just a little bit of a hint. Most of your data that you're keeping around in the system is your code. It is the functions that you've defined that need to stay around because they're going to get executed. They're not changing. So you don't need to be copying them back and forth. There's a very small amount of data in a running system once it's at a steady state that is actually changing. And so if you organize your garbage collection properly, you wind up every time you hit the end of the wall and you need to start back over again, realizing that almost all of it is garbage and there's like 3 or 4 items to copy across. And so if you organize things properly, you can do it that way. So there is very low latency on garbage collection because there's almost never any garbage. And we can talk in greater length about why that is true. It's very extensible. I mean, you can write new things in the language itself, but if you want to get to the C, you can. This is all open source. The hardware is open source as well. The schematics and the bill of materials are all up there on the website. And there's a foreign function interface so you can get to the C library or any other C code you'd like to tack on. I'm not going to go into a lot of detail here except to say that it does have a JIT and it's pretty efficient. And it's about twice as efficient as not having a JIT. And JIT, I mean just-in-time compiling, classic adaptive incremental compilation, that kind of thing. And this is really the end of the basic presentation. Let me just get to the end slide. I've compared it with lots of other embedded Lisps, microcontroller Lisps. It's quite a bit more functional than something like MakerLisp or MuLisp that's available on lots of other platforms. It's a little bit more modern dialect. It has closures. It has macros. It's comparable to a Lisp called FemtoLisp, which has a slightly different approach towards its JIT. They're on par with performance mostly. But I think the main thing I'm trying to get at here is that it's more like Lisp than Forth or Python. So in other words, if you want to have kind of a self-hosted development environment instead of cross-development and kind of clunky downloads and stuff like this, if you want to have a small computer where you're doing all your development on the system itself and you want kind of that rapid prototyping, iterative development, then you're looking at an interpretive environment. And Lisp has some strengths that neither Forth nor Python really have in a very small footprint. These are just some things because I chose to make Lisp the basic system language. These are some pressures that put on the design and kind of caused these kinds of decisions to be made. And again, I'd just like to stress that the particular CPU or the ISA is not really a factor on the machine. And then because of those choices on the machine, when you go back and try to implement the Lisp, then you have these characteristics that you want to do. And this is kind of my last slide. The most important thing, I think, something I'm really stressing when I'm talking to people. And that is that right now, children are starting to learn to program at younger and younger ages. And there's this thing called the law of primacy, which is the first thing you learn becomes your model for everything else you learn. And so, unfortunately, in our computer science education, many of us don't get to the more functional, more interesting, more groundbreaking kind of like big idea programming languages until we're 20 or 30. And by then, we may have had to unlearn all the imperative and command-based and statement-based languages with lots of state in them, and it may be very difficult to switch the model. Like for example, I'm a functional programmer, but I'll never really be an object-oriented programmer. I can do it, sort of, but I don't have it in my heart. It just isn't the way I look at problems. And I think that if people, when they first start learning how to program, have access to some of these better models, it can really change the way they look at the whole problem, and they might be more productive, and it might be mind-opening, and you wouldn't have to kind of jettison so much baggage from some of the other things you learned. So I do think there's a lot of interesting things that might be done teaching computer science for the first time with a simpler, but more focusing on the fundamental ideas. And if we can package this and make this interesting, maybe that will be a useful alternative. When I'm saying in the beginning there were two choices, the first two programming languages that there were Fortran and Lisp. Fortran came first, Lisp came second. Most people went the Fortran route, and all the languages that came from that. And Lisp kind of hung around in the background, but it's still here. And it's still very, very powerful. So that's, Fortran led to 50 years of learning the hard way what you need to learn in Lisp. So the other things that are running on this platform, I've got CPM running. Thanks, Greg, for doing this great work and getting NutX up, and we'll turn that into something that's distributable very soon. It's a very simple system, and I have not nailed down all the resources. So it's using a minimal set of resources on the microcontroller and in the system architecture, so it's kind of wide open. It's very easy to port. But if you just want to look at the hardware and use the hardware as a very vanilla, low-cost, but pretty fast platform, it's useful in those ways too. And whatever you'd like to do with the system, I will help you. So that's pretty much my presentation. Oh, last thing, these are some prices of the various components, but the prices are coming down. And the thing I'd like to point out to everyone here is I have a promotion going for all the Lisp and functional programming groups, and I'm extending it also to this group. And I'm making a special edition of the board. And on the back of the board, I'm going to put the logos of all the participating groups. So it's kind of like promotion of all the groups to all the groups so that you all kind of learn and know about each other. But the board will cost $75 if you get into this, this promotional deal, which will last for a couple more weeks. So how you do that is you just send me an email, and the email's on the back of the business card, and tell me you want to be in this promotion, and I bill you $10 to reserve the board, and then you pay the additional $65 when the boards are ready in a few weeks. So that's my presentation, and I hope we can spend some time playing with the machine in a little while.
Thank you very, very much. I there's this whole backlog of demonstrations and messing around and fiddling that we all want to do. So I suggest we have a maximum of 2 questions, and then we move on to the last presentation before coffee. So do we have any questions? So everyone shell-shocked by such a different system. Yeah.
You said something about the auto configuration. What are you doing? You're sensing
Oh, so what I've got is the CPU card knows whether or not it's plugged into the expansion board. If it's plugged into the expansion board, then it pays attention to jumpers on the expansion board about the routing of certain signals. However, for the power configuration, it doesn't need any of that. It can tell whether you've plugged something into the barrel jack or if you've just got something in the USB port. So the point is, if you plug into the barrel jack, it will not back power your computer. And if you plug into the USB thing and you don't have the barrel jack connected, it'll power that way. So there's a shared 5-volt bus across both boards. And I just wanted to make something that you couldn't plug in and burn it up. So that's what that's about.